Every time a new AI model is released, engineering teams face the same bottleneck, wiring it into their existing infrastructure. You have to physically connect the reasoning engine to your database, your code base, your ticketing system, and your internal APIs. The current standard for making these connections is function calling. You write custom integration glue that teaches one specific model how to talk to one specific tool in your stack. But if your organization runs 5 different models and relies on 20 different internal tools, you're suddenly managing 100 custom API bridges. Multiplying N models by M tools creates a mathematically unsustainable web of fragile endpoints. To stop rebuilding custom integrations, we have to decouple the AI from the data source. This is the primary function of the Model Context Protocol, or MCP. MCP is a transport-agnostic standard. It operates entirely on JSON RPC 2.0 payloads, providing a universal vocabulary that any model can use to communicate with any external system. Instead of maintaining a fragmented mess of custom APIs, developers can plug any AI into any system. It works like a USB-C port for artificial intelligence. This standardized architecture relies on 3 distinct roles: the host, the client, and the server. The host is the user-facing environment where the AI actually operates. This is usually a chat application, an integrated development environment like Cursor, or an internal enterprise dashboard. Inside that host sits the client. This is the internal router. It negotiates the protocol, handles the requests, and routes messages between the AI model and the outside world. Finally, there is the server. This component acts as the external gateway, managing the direct connection to enterprise data and executing specific tool logic. Within this topology, a single host environment is capable of spinning up and managing multiple distinct clients simultaneously. However, the architecture enforces strict isolation. Every individual client maps one-to-one with a specific, dedicated server. This tripartite split ensures a hard physical boundary. The AI reasoning engine inside the host is never directly entangled with the external database it is querying. For these components to exchange data, they require a physical communication mechanism. This is the transport layer. The most common setup is the STDO, or Standard Input-Output Transport. This is used for local, tightly bound server executions, where the client and server are running on the exact same machine. But this creates a critical technical constraint. If you are running an STDO server, you must never use standard output for your server logging. Because the protocol uses standard output to transmit its JSON RPC payload, any print statements or logs sent to STOut will corrupt the message stream and break the connection. To keep the protocol intact, all local server logging in an STIO setup must be explicitly routed to standard error. If you are building remote distributed architectures, you use the alternative transport layer, server-sent events over HTTP. By offering both STIO and HTTP transports, the exact same protocol can power an AI agent locally on a developer's laptop or across global cloud infrastructure. Once the transport layer is established, the server can begin exposing specific capabilities to the AI. MCP standardizes these into 3 distinct context primitives. The first primitive is resources. Resources are strictly read-only, file-like data sources bound by specific URIs. This is how the server feeds raw context, like a local file or a database table, directly into the LLM. The second primitive is tools.
Tools are active functions, but there is a core architectural distinction here. Tools are executed exclusively by the server, not natively by the LLM itself. The model simply asks the server to perform the action. The third and final primitive is prompts. Prompts serve as server-managed blueprints or templates. They allow the server to enforce consistency across repeatable, agentic tasks without relying on the user to manually provide the perfect instruction every time. By standardizing all external interactions into just resources, tools, and prompts, MCP provides every AI model with an identical operational vocabulary. Connecting an enterprise database like a Supabase deployment to an autonomous AI agent introduces severe code execution risks. The most dangerous attack vector introduced by this architecture is known as tool poisoning. Here is how it works. an attacker hides a malicious text instruction inside an ordinary, unverified database row. The LLM reads that row as a standard resource. Once the LLM ingests that poison data, it pulls the malicious payload directly into its active context window, where it is processed as a valid instruction. The hijacked model then attempts to trigger an unauthorized destructive tool execution against the enterprise server on the attacker's behalf. To mitigate this specific threat, enterprise implementations must adopt a zero-trust architecture. This requires strict read-only sandboxing. If you are building an MCP server for local files, you must use absolute paths for your working directories to eliminate the risk of lateral movement across the file system. Finally, there is the ultimate failsafe. Deploying mandatory human-in-the-loop manual approval gates blocks any state-changing execution before it reaches the server. MCP standardizes connections, but it also forces all AI actions through a rigid, observable choke point where strict authorization policies can be applied. Developers no longer need to write custom API glue for every individual AI model on the market. The new development standard is simple. Write your tool integration exactly once as a standalone MCP server. That single server can then be seamlessly connected to any MCP-compatible host interface without altering a single line of the underlying code. This true decoupling eliminates LLM vendor lock-in. Enterprise teams can swap out their foundational models as the market evolves without rebuilding their entire integration layer. By separating the reasoning engine from the data source, the Model Context Protocol establishes the technical infrastructure required for cross-platform interoperability in high-stakes environments.